So here, this hydrolysis reaction, so it depends upon the presence of carboxylic group. So how lipids are getting hydrolyzed? So we know fats, the storage form of the fats that are mainly stored in adipose tissue, and they get stored as triacylglycerol, right? TAG. They are stored in the form of triacylglycerol. That is the storage form of the fat. So when the storage form of the fat is being hydrolyzed, so when the storage form is being hydrolyzed, so our body will look for the alternate sources. When the energy is not sufficient, when our body is not able to provide sufficient energy, so that time it will look for the alternative source. Mainly it gets stored in the form of triacylglycerol. So TAG, we call it as TAG. So triacylglycerol is the main storage form of lipids, fatty acids. So we can write the structure CH2 COOR1. When you consider the structure of triacylglycerol, so it consists of one molecule of glycerol and three molecules of fatty acids. So three molecules of fatty acid and one molecule of glycerol. Together it constitutes the structure of triacylglycerol. So now I am going to the reaction of hydrolysis. How fatty acids are being hydrolyzed? So CH2 COOR1, CHCOOR2, then CH2 COOR3. So this is the structure of triacylglycerol, PAG, triacylglycerol. So what is the enzyme? What is the respective functional group it is involved? So carboxylic group is involved. So here carboxylic group is involved. So here the enzyme is lipase. So hydrolysis, the removal of, that means fatty acid. So it removes during each step. So we know that triacylglycerol is a complex lipid. So it cannot be directly converted to glycerol and fatty acid. So it is a step-by-step reaction, multi-step reaction, wherein it undergoes hydrolysis. So during hydrolysis, so it leaves the fatty acid. So when it leaves the fatty acid, when it removes the fatty acid, so it is removed as CR3COOH. So fatty acid is removed so that the triacylglycerol is converted to diacylglycerol. CH2COOR1, CHCOOR2, then CH2OH. So this forms diacylglycerol. So triacylglycerol on hydrolysis. So here the important functional group which is involved here, it is carboxylic group. So as a release of one molecule of fatty acid, and the enzyme which catalyzes or hydrolyzes triacylglycerol is lipase. Lipase is the specific enzyme which act on lipids, storage form of the lipid, that is triacylglycerol, and so the pH, the enzyme is active. Okay, so it is functionally active. So when the pH is adjusted to 7.5 to 8.5. Okay, so it exerts its action. So the enzyme action, so will get stimulated. So or the enzyme action can be enhanced when the pH is adjusted to 7.5 to 8.5. So that is the optimum condition. So that is the optimum condition where enzyme shows maximum activity. That means it is able to hydrolyze triacylglycerol. So with the removal of one molecule of fatty acid, so it is converted to diacylglycerol. So it releases fatty acid whenever we hydrolyze lipids. So it releases fatty acid. It is converted to, it is hydrolyzed into fatty acid, and that means diacylglycerol. Then further hydrolysis. So further hydrolysis, again this gets hydrolyzed. So this diacylglycerol is further hydrolyzed with the same enzyme lipase, where it releases one more molecule of fatty acid, R2COOH, so that it becomes CH2COOR1, and this becomes CHOH, and third carbon CH2OH. So monoacyl glycerol. So this is monoacyl glycerol. Then further hydrolysis. So again, with the release of the last one more molecule of fatty acid, so which is released as R1COH, and the same enzyme lipase. So here continues the action, so that monoacyl glycerol, with the release of one more molecule of fatty acid or the final molecule of fatty acid release, so it is converted to glycerol, CH2OH. CHOH, then CH2OH, glycerol, right? So when fats are hydrolyzed, when lipids are hydrolyzed, it forms glycerol and fatty acid. So the ultimate end product of hydrolysis of lipid is fatty acid and glycerol, but here it is not single step reaction, it is a multi-step reaction, and this reaction signifies. So it is mainly due to presence of carboxylic group. So which functional group is mainly involved? The main functional group involved in the hydrolysis of fatty acids, hydrolysis of lipids. Storage form of the lipid is considered to be lipids. So this is an enzymatic hydrolysis, and the functional group which is involved in this reaction is carboxylic group, right? So carboxylic group is involved in this reaction. So we need to remember that structure of triacyl glycerol, so it consists of 3 molecules of fatty acid and 1 molecule of glycerol. Together it constitutes the structure of triacyl glycerol. Then further hydrolysis, subsequent hydrolysis of triacyl glycerol, it releases the molecule of fatty acid at each step, so that it forms diacyl glycerol, and then diacyl glycerol with the further release of one more molecule of fatty acid, so it forms monoacyl glycerol, and then final release of fatty acid, so finally it is converted to fatty acid. So this particular reaction, hydrolysis, we call it as enzymatic hydrolysis, because lipase is the major enzyme which catalyzes the storage form of lipids, particularly the triacyl glycerol is being hydrolyzed into glycerol and fatty acid. Okay, so here major group which is involved in this reaction, so it signifies the presence of carboxylic group. So that is very, very important. So we need to highlight the importance of carboxylic group. So what is the significance of this reaction? Okay, so what is the action of lipase? So what are the intermediates which are formed, and what is the functional group which is involved in that reaction? So that is very, very important. Okay. So and next to hydrolysis. Okay. So triacyl glycerol is converted to diacyl glycerol, then monoacyl glycerol, and probably is converted to fatty acid and the glycerol. So this is about hydrolysis, or we call it as hydrolytic reaction. Hydrolysis. Then other than hydrolysis, so the second reaction that comes under carboxylic group is saponification. So we might have discussed the definition, or we know what is saponification, but here we need to discuss. So what are the reactions that comes under saponification? That is very, very important. So here all these chemical reactions, when you write all these chemical reactions, we have to highlight the significance of the chemical reaction, or what is the functional group which is involved in that particular chemical reaction, which is responsible for that particular chemical reaction. So all these reactions, so that comes under reaction due to presence of carboxylic group. So the first one is hydrolysis, where carboxylic group is involved, and even the second reaction, saponification, again the carboxylic group is involved in that reaction. So I hope you might have finished this reaction, triacyl glycerol, hydrolysis of triacyl glycerol. So we'll go with the second reaction, that is saponification reaction. So in saponification reaction, so here the 2 different examples, we are going to see 2 different examples for the saponification reaction. So here in the saponification, so the first reaction is, let me explain the concept of saponification. So what do you mean by saponification? Saponification in a simple way term we can understand. So it is nothing but the process of hydrolyzing fat by using alkali. So when alkali is used for hydrolyzing fats or lipids, so that process of hydrolyzing fats by using alkali, we call it as saponification. So enzymatic hydrolysis, when enzymes are used, we call it as hydrolysis or enzymatic hydrolysis. Similarly, when alkali is used, when sodium hydroxide or potassium hydroxide, when any alkali is used for the hydrolysis process, hydrolysis of lipids or fats, so that process we call it as saponification. The process of hydrolyzing fats or lipids by using alkali, we call it as saponification. So what are the end products that results due to saponification? Okay, generally when fat or lipids are hydrolyzed, so it results in formation of esters of fatty acid and glycerol. But here again, saponification results hydrolysis of fats by using alkali. When alkali is used for this hydrolysis process, so these fats or lipids so are being hydrolyzed and it is converted to glycerol, again the simple form of lipids, and then esters of fatty acid, salts. So or we call it as salts of fatty acid. So it results in formation of glycerol and salts of fatty acid, higher fatty acids. There are two different types of fats. When it consists of salts of sodium salts, then it yields sodium salts of fatty acid, so we call it as hot soap. Similarly, when potassium salts of fatty acid, so we consider as soft soaps. And mainly these salts of fatty acid or the salts of higher fatty acids, so are mainly involved in industries. They are used as lubricating agents. They serve as lubricating agents. They are used in cosmetic industries. They are used in talcum powder industries, and they are used even in paint industries like lead and that means manganese salts of higher fatty acids are mainly used in paint industries. Drying process. To fasten the drying process, they are used in industries. So that is the main significance of the use of the salts of higher fatty acids. And here saponification, example for the saponification reaction. So we are going to see two different reactions. So the first one is, I'll write the first reaction here, CH2COO, C17H33, CHCOO, C17H33, then CH2COO, C17H33. So three molecules. So it consists of three molecules of olein, right? So we consider as triolane. So this is nothing but structure of triolane, right? So triolane. This is structure of triolane. So this triolane, when it is hydrolyzed with sodium hydroxide, so sodium hydroxide is used as the saponifying agent. So used for hydrolyzing this triolane. Okay. So the process of hydrolyzing lipids or fats by using alkali we call it as saponification. So it results in formation of glycerol and salts of fatty acid. So it yields main product here, it is glycerol. So we can write structure of glycerol. So glycerol is a 3-carbon compound, you know, CH2OH, CHOH, then CH2OH. It yields glycerol. So glycerol is considered to be the major products. Apart from glycerol, it yields the salts of fatty acid. So the salt of fatty acid here is, so here CH2COO, C17H33, or else we can write like this, C17H33 COO and A. Sodium, this is sodium OH, right? COO. H, which is the oleic acid, you can write. So this is sodium OH. So this is salts of fatty acid. So this one is salt of fatty acid. So sodium salt of higher fatty acid. So this is nothing but sodium salt of higher fatty acid. So let me explain the reaction once. So here the reaction is saponification. We discussed what is saponification, the process of hydrolyzing fat by using alkali. We call it as saponification. So as a result of saponification, it yields fatty glycerol and salt of fatty acids, higher fatty acids, either sodium salts of fatty acid or potassium salt of fatty acid, depending upon the source of alkali that we use. So here we have used sodium hydroxide for the process of hydrolyzing this fat or lipid, and this is trioluene, and this trioluene is hydrolyzed by using sodium hydroxide alkali, so it yields glycerol and sodium salts of higher fatty acid, and that sodium salts of higher fatty acid is named as sodium OH. Sodium OH. So this is a sodium salts of higher fatty acid. So this is considered to be hard soap. This one is considered as hard soap. Clear, students? So these reactions are very, very important, especially chemical properties. So we have to write down the reaction and then explain what is the respective functional group and what is the significance of the reaction. That is very important. So it yields sodium salts of higher fatty acid, so which we consider as hard soaps. Similarly, the other example is there. One more example is there. So other than this trioluene, so trioluene. So this is with trioluene. So instead of trioluene, so we can take tristyrene. So I'll write the structure of tristyrene here. So C17H35. So trioluene is C17H33, whereas tristyrene is C17H35. Okay, so we can easily remember that. So here this is tristyrene, and so here the alkali used here is not sodium hydroxide. So the alkali used here it is potassium hydroxide. So potassium hydroxide is used as alkali over here, and this is tristyrene. 3 molecules of stearic acid. Okay, so tristyrene. So this hydrolysis is mainly enhanced by potassium hydroxide, and then tristyrene is getting hydrolyzed to yield, it yields or it forms glycerol, and that means potassium salts of fatty acid, because potassium hydroxide is used as alkali source for hydrolysis. So we can write C17H35, it yields along with glycerol, it yields so potassium stearate. So here the salt of fatty acid, higher fatty acid is potassium stearate. So this potassium stearate is considered to be soft soaps. So the previous one is example for hard soap, that is sodium salts of fatty acid, higher fatty acid, sodium OH, and this one is potassium stearate, C17H35COOK, potassium stearate, which is considered to be soft soaps. So 2 examples we have discussed. One is hard soap formation, and second one is soft soap formation under saponification reaction. And mainly this reaction signifying the presence of the important functional group. So which group is mainly involved? Which group is replaced? Carboxylic group is involved. Carboxylic group is replaced. So this reaction signifies the presence of carboxylic group. So that is very important. So each and every reaction we need to understand the significance on what is the functional group which is involved in that reaction. So that is very, very important. Okay, so one is hard soap formation and the second one is soft soap formation. So that is saponification. So under reaction due to presence of carboxylic group, first one is enzymatic hydrolysis, and the second one is saponification, and third one is rancidity. So third reaction here, it is rancidity, and particularly we call it as hydrolytic rancidity, right? So let me explain hydrolytic rancidity. Hydrolytic rancidity, what is rancidity? Generally, rancidity we can recognize easily by its order, right? Bad order, right? So when you store a fat, or even if you do refrigeration is a process by which we can prevent the process of rancidity to some extent. Okay, so we can delay the process. So removal of water molecules, exclusion of water, right? So rancidity, mainly hydrolytic rancidity. So it is mainly caused by growth of microorganisms when microbes are grown over the surface of fats or lipids. So some of the microbes which are able to hydrolyze the lipids or fats because they are able to secrete the enzyme lipase. Microbial lipase, we know the source of microbial lipase, Aspergillus niger and other microbes and even some bacteria are able to secrete so this enzyme lipase. We know the source of lipase. So the microbial source, so which act on the substrate, that is fats or lipids. So thereby it hydrolyzes. It starts hydrolyzing the fats or lipids. So it oxidizes the fats or it oxidizes the lipids. It does partial hydrolysis and partial oxidation of fats. So due to partial hydrolysis and partial oxidation of the fats, so these lipids or fats, when it is hydrolyzed by microbial lipase, so it is converted to short chain fatty acids. It results in formation of incomplete products, not complete products. So that it yields short chain fatty acids. So these short chain fatty acids, as a result of the action of microbial lipase, it gives bad odor and taste due to partial oxidation and partial hydrolysis. So it gives bad odor. It imparts bad odor and taste to the fats or lipids. So that process is called rancidity, which is caused by the growth of microorganisms. So that type of rancidity is called hydrolytic rancidity, and where the major functional group here it is carboxylic group. So it oxidizes the carboxylic group. So carboxylic group is involved in that process of hydrolytic rancidity. So that type of rancidity we call it as hydrolytic rancidity. So hydrolysis, saponification and hydrolytic rancidity. So where we have to remember the major functional group which is involved in all these three processes is carboxylic group. Okay, hydrolysis, enzymatic hydrolysis, saponification, and then hydrolytic rancidity, where this carboxylic groups plays a significant role and is mainly involved in all these reactions. So that is about reaction due to carboxylic group, right? So that is due to reaction due to carboxylic groups. And reaction due to double bonds. So double bond is very, very important. So when you say double bonds, so when fatty acids have double bond in their structure, generally we assume or we consider as unsaturated fatty acids. So they are considered as unsaturated fatty acids. I just already mentioned in the property, physical property, that plant oils are considered to be the rich source of unsaturated fatty acids, particularly essential fatty acids. Essential fatty acids are rich source of this unsaturated fatty acids. What do you mean by essential fatty acid here is that essential fatty acid, maybe I'll just mention about the sources. Soybean, corn oil, cotton oil. So all these are rich sources of the essential fatty acid. The percentage is very higher, 75%. Corn oil, it is 50%. Cotton seed oil, it is 40 to 45%. They are considered to be rich source of essential fatty acids. So what do you mean by essential fatty acid? Essential fatty acid has nutritional importance. Okay, so they play a nutritional importance. And these essential fatty acids are widely distributed in plant sources, especially soybean, corn, and cottonseed oil are considered to be rich source of essential fatty acids. Polyunsaturated, they consist of polyunsaturated fatty acids, the major constituents that constitute the essential fatty acid are nothing but polyunsaturated fatty acids. So unsaturated fatty acids, specifically polyunsaturated fatty acids. That means it contains more than one double bond in its structure. So polyunsaturated, linolenic acid, and arabidinic acid. All these are familiar example. Even oleic acid. So oleic acid is not a polyunsaturated fatty acid. Oleic acid is a monounsaturated fatty acid, whereas linolenic and the arabidinic acid are so familiar examples of polyunsaturated fatty acid, which are the main source of essential fatty acids. So which are the chief constituents which constitute the essential fatty acids. So essential fatty acid plays a significant role. The functional role. We know the functional role of essential fatty acid, it includes. So they are considered to be the essential components. They are the supplements of the tissues. They are considered to be the supporting elements of the tissues. They are considered to be the supporting structure of gonads, reproductive organs. They play important role in reproductive function as well. And moreover, so it is also involved in, they are considered to be rich source of polyunsaturated fatty acid, where it lowers, is involved in lowering the serum cholesterol level. So it plays a significant role. Essential fatty acid plays a significant role in lowering the serum cholesterol level. So all these functions are the important functions which are carried out by this essential fatty acid. So why we are talking about essential fatty acid is that. So I just briefed. So what are unsaturated fatty acids and unsaturated fatty acids, especially polyunsaturated fatty acid. What is the significance of polyunsaturated fatty acids? So polyunsaturated fatty acids are the chief constituents that is involved in formation of essential fatty acids. So now we are going to see the reactions, chemical reactions or the chemical properties. So that comes under double bonds. Okay. So under that we have hydrogenation and halogenation. And then rancidity, we also see rancidity, hydrogenation, and then other one is halogenation, and then now, so we take this rancidity, oxidative rancidity. So this is called oxidative rancidity. So oxidative rancidity, and the other one is oxidation. So four reactions that comes under reaction due to presence of double bonds. So first we finish reaction due to presence of carboxylic group. Now reaction due to double bonds. So double bond where it is present, so it is present mainly in the unsaturated fatty acids. So we will go one by one. So with the reactions due to presence of double bonds. So under the double bonds, the first reaction that we are going to see is hydrogenation. Hydrogenation, in a simple way, we can understand addition of hydrogen. Okay, it takes up hydrogen, unsaturated fatty acids. We know what are unsaturated fatty acids. They have double bond in their structure. They possess double bond in their structure. So those double bonds are ready to take up the hydrogen. Okay, so if more double bonds are there, it takes up more hydrogen. So it takes hydrogen so that unsaturated fatty acids are converted to saturated fatty acids. So that is the significance of the hydrogenation. What is the significance of hydrogenation? Hydrogenation is a process which takes up hydrogen readily at the double bond. At the same time, it converts the unsaturated fatty acid into the saturated fatty acid. And the main functional group involved here is double bond. So it depends on presence of double bond, and that too only unsaturated fatty acids are involved in the hydrogenation reactions. So now let us see this hydrogenation. So under that, first we can write oleic acid. See the structure of folic acid. I am writing the structure of folic acid. So CH 3CH2 CH double bond CH2 COOH. So this is the structure of folic acid. Folic acid is an unsaturated fatty acid. Folic acid is an unsaturated fatty acid, monounsaturated fatty acid. It is not a polyunsaturated fatty acid. It is a monounsaturated fatty acid. So it contains only one double bond in its structure, right? So this is folic acid. Folic acid. So what is the reaction now? So the reaction is hydrogenation, addition of hydrogen. So where hydrogen is added? So hydrogen is added probably in the double bonds. So when one double bond is present in the structure of unsaturated fatty acid, it readily takes up two hydrogens. It readily takes up two hydrogens. So this CH double bond CH becomes CH2 CH2. Rest all it is same. Rest all it remains same. CH2 7 COOH, and here the other side CH2 7 and then CH3. Right? So it takes up hydrogen at the double bonds. So only one double bond is there, and this is folic acid. Only one double bond is there. So this unsaturated fatty acid, when it undergoes hydrogenation, so it readily takes up hydrogen, right? So it takes up two hydrogen molecules. So when it takes up hydrogen, CH double bond becomes CH2, and then folic acid is now converted. I mean, the unsaturated fatty acid is converted to saturated fatty acid because there is no double bond now. CH double bond becomes changed to CH2. So there is no double bond. So it is converted. Conversion of, so this reaction signifies conversion of unsaturated fatty acid to saturated fatty acid. So it becomes stearic acid. So conversion of folic acid into stearic acid is a familiar example of hydrogenation. It's a familiar example of hydrogenation. So this reaction is very important. So whenever you write any reaction, you write along with the reaction, you have to write the significance. You need to highlight the significance, and you need to specify what is the group, functional group which is involved in that reaction. So on that aspect, so you have to give the explanation for each reaction. So that is very important. So folic acid is converted to stearic acid. So folic acid is an unsaturated fatty acid. It readily takes up hydrogen at the double bond, so that it is converted to saturated fatty acid. So because it's a monounsaturated fatty acid, so conversion of unsaturated fatty acid to saturated fatty acid. So that is the significance. And the main functional group involved, or the functional group involved in this reaction is double bond. It depends upon the presence of double bond. If one double bond is there, it takes up two hydrogen. If two double bond is there, it takes two more hydrogen. Okay. So that here the familiar example is considered to be folic acid to stearic acid. So this is example for, so that is hydrogenation. So we need to know definition and what is hydrogenation, and the example for hydrogenation is conversion of folic acid to stearic acid, and it signifies the conversion of unsaturated fatty acid to saturated fatty acids. That means unsaturated fatty acids mainly present in plant oils, so that plant oils, once they are converted to saturated fatty acids, okay, so that can be converted to saturated fatty acids. So it helps in the conversion of, that means unsaturated fatty acid to saturated fatty acid. That is the main significance, and it is mainly due to presence of double bond. So here hydrogenation, and this is hydrogenation, and the other one is halogenation. Halogenation, instead of hydrogen, it takes up readily halogens at the double bond. Same reaction we can give example given for halogenation, but instead of hydrogen, it takes up halogens, chlorine, bromine, iodine. Okay, it takes up fluorine. So it readily takes up halogens at the double bond. So only that is the difference. So instead of hydrogen, it readily takes up halogens at the double bond. So it becomes CHI, and here one more. So iodine, it readily takes up iodine. I mean halogens at the double bond. So halogenation is the process of taking the halogens readily at the double bond. So wherever the double bond present or exists, particularly in the unsaturated fatty acid, it readily takes up the halogens at the double bond. The process of taking halogens at the double bond, so that is because presence of the double bond. It depends on the presence of number of double bond. When more double bond is there, it takes up more iodine at that double bond, so that here this converted. So here oleic acid is converted to diiodosturic acid. So it takes up 2 molecules of iodine, so that it becomes diiodosturic acid. So oleic acid is converted. Oleic acid is a monounsaturated fatty acid. It contains only one double bond, and then when it takes up iodine, so it takes up 2 molecules of iodine at the double bond, so that CH double bond becomes CHI and CHI, so that it is converted to diiodosturic acid. Diiodosturic acid. So this is a familiar example here for the halogenation reaction. So conversion of oleic acid to diiodosturic acid. Okay. So diiodosturic acid. So another one is linoleic acid. We can even write linoleic acid. There it forms tetraiodosturic acid because 2 double bonds. It's a polyunsaturated fatty acid. It has 2 double bonds. Instead of 1 double bond, it has 2 double bonds. So each double bond, it takes up 2 molecules of iodine. So when 2 double bond is there, so it takes up 2 iodine molecules, 2 iodine molecules, so that it is involved in formation of tetraiodosturic acid. I'll be writing the structure of tetraiodosturic acid also. So I think this one is clear now. Oleic acid to diiodosturic acid. Instead of hydrogen, here the iodine is replaced. I mean the halogen is replaced. So here now I'm just writing the structure of linoleic acid. Just listen the structure of linoleic acid. So linoleic acid is a polyunsaturated fatty acid. Polyunsaturated means it contains more than 1 double bond. It contains 2 more than 1 double bond. So CH3, CH2, CH double bond CH, CH2, then again CH double bond CH, CH2, 7, COOH. So clear students? I'll tell you the structure. Linoleic acid. Linoleic acid, right? It is a polyunsaturated fatty acid. Polyunsaturated fatty acid, right? It's a polyunsaturated fatty acid. CH3, CH2, 4, CH double bond CH, CH2, CH double bond CH, CH2, 7, COOH. Okay, so this is the structure of linoleic acid. Here 1 double bond is there, here 1 double bond is there. So 2 double bond. It contains more than 1 double bond. So it comes under the category of polyunsaturated fatty acid, right? So when it takes up iodine, now we'll be writing the products. So what will be the product that forms? So as a result of this halogenation process, when this linoleic acid takes up iodine, so here it readily forms. Now I'll be writing the structure of the end product. CH3, CH2, 4, CHI, single bond CHI, then CH2, then CHI, CHI, then CH2, 7, COOH. Right? Now I hope it will be clear. Right? CH3, CH2, 4S, CHI, CHI, because this CH double bond CH becomes, it takes up iodine, so it becomes CHI and CHI single bond, then CH2, then here again it takes up double bond, particularly iodine at the double bond, so 2 more molecules of iodine are added, already 2 molecules of iodine and again 2 more molecules, so totally it takes up 4 molecules of iodine. So when it takes up 4 molecules of iodine, So in the previous reaction, uric acid is converted to diiodosturic acid because it takes 2 molecules of iodine, whereas here it takes 4 molecules of iodine. So when it takes 4 molecules of iodine, so this structure will be named as tetraiodosturic acid. Tetraiodosturic acid. Steric acid. Tetraiodosturic acid. So only linoleic acid is a polyunsaturated fatty acid. So when it undergoes halogenation, so this is halogenation. We are discussing halogenation. So it readily takes up 4 molecules of iodine at a double bond, so that it is converted to tetraiodosturic acid. So that is about halogenation. So halogenation, we discussed 2 reactions. One is oleic to diiodosturic acid, and the other one is linoleic acid to tetraiodosturic acid. Okay. So that is halogenation. Oxidative rancidity. What is oxidative rancidity? So the previous one, the rancidity, whatever we discussed, was hydrolytic rancidity. That is caused by growth of microorganisms. Due to the growth of microorganisms, the enzyme gets secreted by the respective microbes, so that it hydrolyzes. So it partially oxidizes and hydrolyzes the fats or lipids, so it becomes acidic. It converts to the hydrolyze, or it undergoes the partial oxidation. Okay, so that is how it becomes yellow in color. Okay, generally pure fat is colorless, but when it undergoes oxidation or hydrolyzes, partial oxidation or partial hydrolysis, it becomes acidic and it appears more yellow in color. That is because of partial oxidation. Same way here, the rancidity. So here the rancidity, oxidative rancidity. So specifically it is caused by, this is a spontaneous process. Spontaneous process by which the oxidation of the fatty acid or fats, mainly due to the oxidizing agents which are present in the atmosphere. Oxygen is used as an oxidizing agent. So it's a oxidizing agent. So spontaneously it oxidizes the atmospheric oxygen. When the fat is exposed to the atmospheric oxygen, so it serves as an oxidizing agent. So thereby it oxidizes, it partially hydrolyzes the fat into, that means fatty acid, short chain fatty acid. So it is converted to short chain fatty acid. So it results formation of short chain fatty acid. It leads to the partial oxidation. So that type of the partial oxidation, it results formation of short chain fatty acid, which gives bad odor and taste to the fats, and that process we call it as oxidative rancidity. That is due to spontaneous agents which are present in the atmosphere. Familiar example is atmospheric oxygen. So that type of rancidity we call it as oxidative rancidity. It cleaves the double bond. So the agents that cleaves the oxidative agents, it cleaves the double bond. So it partially hydrolyzes and oxidizes the fats. So that type of rancidity we call it as oxidative rancidity, and mainly the double bond is involved. The functional group, the major functional group involved in the oxidative rancidity, again it's a double bond. And here oxidation, how fats are getting oxidized. Different oxidizing agents are there. Okay, I just mentioned oxygen is an oxidizing agent. But then, so where this oxidation of fats takes place. So oxidizing agents, that means spontaneous oxidizing agents. So when fats are getting oxidized, so here the different type of oxidizing agents are there. I'll just give an example for this spontaneous oxidation of fats. So here when you consider double bond, CH, it's an unsaturated fatty acid, CH2 and CH2. So this we consider, this is the representation of unsaturated fatty acid, isn't it? Because it contains double bond in its structure. So here when it is oxidized by, so O3, right, ozone, it's an oxidizing agent. So here it oxidizes fat. So it becomes unstable, it forms unstable structure. So this unstable structure, so we name it as ozonoids. So this is an unsaturated fatty acid. This is representation of unsaturated fatty acid. So this unsaturated fatty acid, with the action of ozone O3, so it forms unstable compound ozonide, and then further hydrolysis. Again, it is hydrolyzed. So further hydrolysis, it results with formation of short chain fatty acids. See, fatty acid, short chain fatty acid, it can be represented as CH2, C double bond O H. Again here, C double bond O H, CH2. These are short chain fatty acids. So this is one short chain fatty acid. This is again short chain fatty acid. So these are short chain fatty acids. Short chain fatty acids. Short chain fatty acids. So when fatty acids are oxidized, so ultimately this converted to short chain fatty acids. So there are different type of oxidizing agents. It can be O3, ozone, or it can be KMnO4. Even KMnO4 is used as potassium permanganate. KMnO4 is used as an oxidizing agent. So it cleaves the double bonds. So here all these reactions, so that comes under reaction due to double bond, presence of double bond. So here all these reaction it signifies, especially mainly due to presence of double bond. So another familiar example for oxidation is conversion of oleic acid. I already drawn the structure of oleic acid. So this oleic acid is converted to, so dihydroxystearic acid is converted to dihydroxystearic acid. So all these reactions are there in the LMS. So you can go through the reactions, especially when you write chemical properties. So we have to write the reactions with structure. Oleic acid is converted to dihydroxystearic acid. Dihydroxystearic acid, right? So here the oxidizing agent is KMnO4. That is potassium permanganate is an oxidizing agent. Okay. So here dihydroxystearic acid, how can you write dihydroxystearic acid? CH3, CH2, 7. You know the structure of oleic acid. That's why I didn't write the structure here. Oleic acid. So CH3, CH2, 7. Double bond will be there. CH, double bond CH. So here, so it takes up hydroxyl group CHOH, CHOH, and then CH2, 7COOH. Okay. So this forms dihydroxystearic acid. So that is reaction due to double bond. So the last one, I'll take 2 minutes, students. I'll just finish up the chemical reaction. So the one is dehydration reaction. Reaction due to presence of hydroxyl group. Reaction due to presence of hydroxyl group. Under that one is dehydration reaction. I'll just write the dehydration reaction. So it is very, very important. Okay. So this one is oxidation. Whatever we discussed was oxidation. And last reaction, a reaction due to presence of that is hydroxyl group, OH group. So under that dehydration reaction. So I'm just writing the reactions of dehydration reaction. So that is nothing but glycerol. We all know that glycerol, CH2OH, CHOH, and then CH2OH. And here the dehydrating agents. So this is structure of glycerol, and the dehydrating agent is sodium hydrogen sulfate, NaHSO4, or potassium hydrogen sulfate, KHSO4. So any one can be used as dehydrating agent. So what happens here? So here it forms CH2, double bond CH, CHO will be removal of water molecules. So as a result of removal of water molecules, so it results with formation of unsaturated aldehyde, which is named as acrolein, right? So dehydration is nothing but removal of water. So the reaction is dehydration, and so that represents or that signifies the presence of hydroxyl group. So hydroxyl group is involved. So here the water molecule dehydrating agent is sodium hydrogen sulfate or potassium hydrogen sulfate. So glycerol is converted to unsaturated aldehyde. Aldehyde group is located here down, CHO. So acrolein. So the formation of acrolein is a very important step. So as a result of acrolein formation, we come to know that so fat that conforms that fat has glycerol content, or the glycerol content of fat can be conformed by the formation of acrolein. So the formation of acrolein which confirms the presence of glycerol in the fat molecules. Okay, with the removal of water, dehydration reaction. So the reaction is conversion of glycerol to acrolein by dehydrating agent, where it removes the water molecules, and the group which is mainly involved here in this reaction is hydroxyl group, OH group. Okay, so that is the significance. So with this, chemical properties or chemical reactions of fatty acid is over. So next class, probably we can start the classification of lipids, and particularly we are going to concentrate on compound lipids. We don't have much of simple and the derived lipids. Particularly, we are going to concentrate on individual, that means compound lipids, their structure and the biological importance. So that's all for today. So if you have any doubts, you can unmute yourself and ask. Otherwise, I can wind up the class. I hope it will be clear. So today we discussed the chemical properties or chemical reactions of lipids. It's a very important topic, so that we have to write down the reaction and we have to highlight the significance of the reaction and what is the responsible functional group which is involved in those reactions. So that is very, very important. So you please go through the LMS content as well. Okay. So students, if you have any doubt, you can ask. Understood, students?
Yes, sir.
Okay.
Yes, sir.
So if you have if you don't have doubts, I can end the class.